Hello, hello. Here we go. Chapter 10 review for the test. This is going to be amazing. Question number one, please be careful that um, all you're doing is determining the correct procedure. Essentially, you are naming the test. That is all. Okay? So for part A, it says, and I highlighted, do people smoke less when cigarettes cost more? So right off the bat, that is giving you kind of a claim. This determines that there is a null and an alternative, so it makes it a test. Okay. And looking on, I've highlighted some important things. They are recording the number of cigarettes that each person smokes every day. So that makes it a sample mean. So see red and red. It is not a proportion. Okay. But now here's the key on this one. It's the number of cigarettes that each person smokes per day over a month period. And then they started taxing the cigarettes, 30%, and then they recorded the same person for another month after the tax was imposed. So there's kind of like the number of cigarettes without a tax versus the number of cigarettes with the tax. So um, you're kind of comparing the change in the number of cigarettes for one person, like a before and after. So that's always like a matched pair t-test. It's not a proportion test. B, so percent stood out to me right away. Percent of senior citizens who attend a play. And so percents are as proportions, okay? And then they're comparing senior citizens versus people in their 20s. So you have two samples, two groups. And it is an interval because there's no claim that we're testing. It just says how much greater is the percent of senior citizens versus people in their 20s. So it's not a test because there's no claim. C, you have data on rainwater collected at 16 locations um, in the mountains of New York State. So this is just a single sample, one sample. This might throw you off. You're like, what? Everything in chapter 10 is two samples. Well, yeah, but we gotta always circle back and review from the past. So it's a one sample. It is an interval. Again, if you keep reading here, it's not telling you or asking you to check anything or confirm a claim of any kind. It just says there's acidity of water and um, estimate the average acidity of the rainwater. That's it. So average again is a mean. So it's a T. T's are for means. The letter D, we have two equal sized groups. So I highlighted that in purple. So it's a two sample. Um, and what are we recording? We are recording the time required for each volunteer to carry out a series of routine calculations. So they're recording a number or an amount, which is a mean, like the average amount of time it takes somebody to carry out a task. Okay. Um, and then they are comparing the two groups. So it's two samples and it's means. Again, I believe it's an interval because it never says anything like we believe one group to like we don't believe calculator A is any better than calculator B. We believe there's going to be a difference. Never says that. So they're just saying, hey, create an interval to determine what the difference is. Number two, this is about seat belts. Apparently, they've chosen drivers. What is this one again? Sorry, I filled out the key and now I forgot. Uh, oh, yes, this is drivers in New York versus Boston. They picked female Hispanic drivers for this study for some purpose. I'm not quite sure why. And they recorded how many of them wore their seatbelt. So, is this an experiment or observational study? Um, it's observational. Um, the drivers were not given a treatment. It just says here are data from observing, I mean, there's the word observing these females in these two cities. So they called them up and said, do you wear your seatbelt? Okay, so it's an observational study. And also the drivers were not assigned to live in a certain city. B, it's a lot of work. It's the full construct and interpret an interval, a 95% interval for the difference um, of the drivers who wear seatbelts in both cities. So first off, I define my variables. You should always do this. Some of you kind of skip this. I called P1 the proportion of females who wear their seatbelt in New York, and then I just did a bunch of quotes, ditto marks for P2 for the females that live in Boston. The name of it is a two sample because you got two cities. It's a Z interval for the difference of P1 minus P2. Or you could just throw the word two sample proportion. You could throw proportion in right here. Random, it's set up here that it was random. Where did it say that? Random samples, so it said that. Is it approximately normal? Well, you have your successes and failures to find. So 183 successes. Well, how many failures is that? Quick calculator work here. Out of 220 minus 183. Oops, I can't. Missed a button. So there's my 37 that I got there. Then 117 minus 68. So that's how I got these four numbers right here. All of them are at least 10. That's called large counts if you were trying to remember that vocab word. Are they independent? You guys, are these samples less than 10% of all the Hispanic females in these cities? These cities are massive. There's like 30 million people or something like that. But to show the work, you multiply them by each sample by 10. You get about 2,000 and about 1,100. Is that less than all the Hispanic female drivers in New York and less than all the Hispanic female drivers in Boston? Don't skimp on this, you guys. List your population, refer to what it is. Again, it convinces the grader, hey, this person knows what we're doing here. So those are your conditions. Then here's your formula. Okay. Let me connect some of the dots here. Um, this first one is P1. Okay. In your formula, this is P1 minus P2. So P1, you can just do a little math with these numbers and divide it on your calculator. That's 0.832. You need to write this out. P2, same thing with these numbers. Bada bing, bada boom. 196 comes from a 95% Z star. Okay. Z star for 95%. Then, again, inside the square root, P1 is used for the first one. So put P1 there, and then 1 minus P1. You can zoom in on that if you need to. And then the sample size for the New Yorkers. And this is P2 and 1 minus P2, and the sample size for Boston. You need to write this out. You need to plug the numbers in. Then you can use your calculator, and I'll remind you how to do that here. Stat tests. It is capital B, and then you need to plug in the numbers. So 183 out of 220, 68 out of 117. And the percentage is 95. Boop. So you can see there that on the calculator agrees. 0.14. Well, I guess I rounded mine to 9 for some reason, but I'd let that go. And 0.353 right here. Okay, and then you conclude with a sentence. We are 95% confident the true difference in proportion of Hispanic females who wear their seatbelt in these two cities, New York minus Boston, is between those two numbers. Okay? Then lastly, it's asking you in part C, based on the laws in these cities, we would expect a smaller proportion of drivers to wear their seatbelts in Boston than New York. Does the interval give good evidence that this is true? We would expect Boston's to be smaller. Well, is it smaller? It looks to be smaller. but are we convinced that when we subtract these two, if it is smaller, you should always get a positive number? And if you look at your interval, zero's not in there, okay? So since zero's not in there, we have significant evidence that a higher proportion of women in New York wear their seatbelt than in Boston. So we can confirm that claim. All right, number 3, expensive ads. This is a long paragraph about advertising. And can other information undermine the effect of advertising? So this is like there's subliminal messages going on, I believe. Oh, no, sorry. I got my stories mixed up. The subjects were 90 women from the clerical and administrative staff of a large organization. They all read an ad that described a fictional line of food products called Five Chefs. The ad also described the major TV commercials that would soon be shown, an unusual expense for this type of product. The 45 women who were randomly assigned to the control group read nothing else, and the 45 women in the undermine group also read a news story headline, "No link between advertising spending and new product quality." All the subjects then rated the quality of the Five Chefs products. It's kind of a strange context, but there you have it. The mean quality ratings were significantly lower in the undermine treatment. So the women that were told there's no link rated them much lower. Their average was 4.56, and the control group was 5.05. Here's your statistic, and here's your p-value. It's less than 0.001. Explain why random and independent are met. It's random because it was stated that the sample was random, okay? It's independent because 45 women is less than 10% of the females in this large organization. You could even say, I guess, 90 women, that would also be less than 10%. If it's a large organization, like a massive company, there's probably more than 1,000 people in it, okay? B, the distribution of responses is not normal because there's only a 7-point scale. Why is it still proper to use a 2-sample t-test? So they're trying to key you into the normal condition, okay, because we just did random and independent. So what's left? Normal. And even though the responses were not normal, if our sample is large enough, if it's greater than 30, the CLT will be met and we are good to go. So that explains why it's still proper to move on. Interpret the p-value. So this we need to take time on because it was on the Chapter 9 test and it could be improved upon. So essentially, folks, you always start with this. If there is no difference, if our null hypothesis is true, if the averages are equal, in other words, if you subtract them and you get 0, if that's true, okay, if there's no difference in the ratings of the product under the 2 treatments, okay, that's essentially saying if the null is true, then there's a 1% chance, actually a less than 1% chance, of observing a difference as large or larger than the one in the random experiment. So here's their experiment, right? They got a statistic of 264, and the probability of that is 0.01 or 1%. So if this is true, we will only get samples like this 1% or less of the time. That's what the p-value means. Number 4. This is they are recording the progress of men. Is this men? This is men versus women. That's right. And they each took the NAEP, National Assessment of Educational Progress test. It's a young adult literacy assessment. Okay. They had 2 groups, 840 men, 1077 women. Here's their data. Their averages and their standard deviations are listed. So there we go. And the question is there a difference between the average for men and women at the 1% significance level? Okay, so we're doing a full test. Okay, so I identified my variables with subscripts, M for men, W for women. The null is that there's no difference when I subtract them. Now this is the alternative here, is that they're not equal. It did not say are men greater than women or are men less than women. It just says, is there a difference? The name of it's a two-sample t-test for the difference of the means. Random was stated in blue right there. In normal is that both of these for t-test, they're plenty big. 840 and 1077 are way bigger than 30. So the CLT is met. Independence, multiplying each sample size by 10 right here, you get 8,400 and you get these two numbers. But this is, our population is like people 21 to 25 years old. So that's way less than that. It's all the males and all the females who take this test, or maybe more generally, all the people in this age category. Then you do your work. It's a T, it's a test statistic. Here's X1, here's X2. You have to fill this out. You're subtracting the null, that the difference is 0. Then your first standard deviation and your sample size for men go there, and likewise for the females, 57 and a half and 1077. Okay, you need to fill this out. Take your time, write that down. You don't necessarily need to crank this out by hand. I would use my calculator. It would be good to always list the degrees of freedom to show them I know what I'm doing. You look at the smaller sample size, not the bigger one, and you subtract 1. So 839. Let's just show it on the calculator because I would do this on the test. I would, again, set that up by hand and then do the rest on the calculator. So this is a two-sample t-test. This is number 4. And you plug in all the numbers and just be careful that you don't screw up. Like I just did. It's like I'm jinxing myself. 59.2 was the standard deviation for the males. 274.73. Boop. Oh, and 57.5 and 1077. Notice on the options there in the right below where the cursor is right now, it says data or stats. I have to do stats for this because I don't have all the data. I just have the summary statistics. So you can see the t-value matches up with right there, -8.6. I guess I rounded it a little bit funky again, okay? And my p-value, 0.38. Oh, looks like I rounded it a bit odd again. I think I actually took this from the textbook, but you won't be knocked or marked down for this is the thousandth place, you guys. That's okay. Do notice that this is a two-sided test. A common mistake kids are going to make is they're going to click here and do the one-sided test, and then they would cut this in half. Even if you do the greater than test, that makes it, you can see the picture up there. You can see how you can actually get like 3 different values. Doing the greater than side, it's like 0.80, and here's 0.19, and then here's the correct answer, 0.38, which does impact your conclusion, right? So p-value is pretty big no matter what. I don't think, maybe it doesn't fully impact your conclusion, but p is bigger than alpha, because what was alpha again? It said the 1% level. So alpha is 0.01, and we've got like 0.38 going on right here. So we fail to reject the null when that happens, okay? Maybe this would be a good time to remind you of this little handy dandy picture I've made for you guys, right? Here's alpha, 0.01. Up here, you fail to reject the null. And down here, you reject the null. But where are we? This is way up here. It's way higher than 0.01. Now, what does that mean? Okay, so we are not rejecting this, so the evidence kind of supports this. Or you could also say, we do not have evidence of this. We do not have evidence that there's a difference. And that's the way I phrased it. We do not have enough evidence that males and females have different scores on this test. All right, number 6. Um, this, again, is just saying, don't do the whole test, guys. Just explain why it's not safe to use the methods of this chapter to perform inference, to do a test, or to do an interval. So in other words, which of the 3 conditions is not met? Okay. This first one is about Lyme's disease, and ticks are infected mainly by feeding on mice. So more mice result in more infected ticks. So experimenters studied 2 similar forests, okay, a year when the acorn crop failed. They added hundreds of thousands of acorns to one area to imitate an abundant corn crop while leaving the other area untouched. I'm reading this going, oh my gosh, what is all this for? I'm looking for what matters. Okay, here's what matters. Ooh, here we go. The next spring, 54 of the 72 mice that were trapped in the first area. Okay, boom. I don't even want to read more. I just know, okay, there's my first sample. Okay, versus 10 of the 17 mice in the second area. Boom. Sample number 2. Okay, but that's all I need, folks. Normal condition is not met because I need at least 10 successes and 10 failures. How did I know it was maybe I should not gloss over this. This is a proportion, right? It's like 54 of the 72. That's a proportion. 10 of the 17, okay? That's a proportion. Um, but we're almost there, right? 54 is good. 54 plus 18 is 72. 10 just makes the cut, but 17 minus 10 is 7. So that's the failure, so to speak, in that sample. So I had one of them that didn't make it. This next one, again, I'm looking for what matters. My eyes immediately go here. They have a random sample of 31 kids. I'm like, ooh, they're trying to trick you. 31's bigger than 30. Great. What are they recording? Let me back up, I guess. They believe females text more than males. So they got 2 groups. They're going to ask them, how many texts do you send? It's a number. So this is a t-test, right? So it's a CLT situation, right? But here's the kicker. This is split up into 2 groups, 15 and 16, and both of those are not big enough. So then they're like, oh, well, look, guys, we made bar graphs, or we made box plots for both, but they both got issues. The males have outliers, so that's a big no-no, and the female one looks to me to be skewed right, so that's bad. So it's not normal. Okay. Um, Last 2 questions. This one, it says, each day I'm getting better at math. This one is the one I was thinking earlier. This is the one where they have kids that failed math. Um, they agreed to take part in a study. Okay. They all received daily subliminal messages flashed on a screen too rapidly to be consciously read. Okay, seems kind of weird. Then there's a group of 10 kids at random that was exposed to each day I'm getting better at math. Okay. So there were 18 kids, 10 of them got this subliminal message that each day I'm getting better at math. The 8 kids in the control group did not get that message. They had a neutral message that flashed on the screen that said, people are walking on the street. Okay, random, but I guess that has no impact on their math skills, and probably wouldn't. Okay, so, and then all 18 kids were in the summer program designed to raise their math skills. So they're comparing the treatment group, each group had a pre-test and a post-test, to the control group, and which group made more progress. Okay? Hoofda. Let me come back to this. Part A says, write a few sentences comparing these 2 groups. They give you the box plot. C, by the way, this is for the control group. T is for the treatment group. Anyway, so I just pulled out a few things that I noticed. The treatment group here just seems to be higher scores, seems to have higher scores. Their medians are much higher, like this is 7 versus 11 or 12. Even their Q1s are higher, their Q3s are higher, like everything's higher. Um, this one also seems pretty darn symmetric. This is what I wrote right here. Whereas the control group, like this box is a little bit bigger than this box. So I was like, yeah, maybe it's kind of skewed right. I'm just comparing them. Um, okay, part B says make a 90% confidence interval. All right, I define my variables. T is the mean difference in scores in the treatment group. C is the mean difference in the control group. Okay, the name is a two-sample T interval. Random was stated. Normal, it's like, uh-oh, these are too small. Neither one is bigger than 30. But look, guys, they gave you the box plots. And neither one shows it being skewed. And I don't see any stars, so there's no outliers. So we can proceed. Being independent, I just wrote this time, each student's scores are independent of another's. All right, then doing the work. All right, where in the heck did I get these numbers? I took out my calculator. And I took some time and I plugged them in. So for list 1 is the pre-test, list 2 is the post-test. I'm going to go here for list 3 and do L2 minus L1. Like, how much did they improve? And then over here on list 4 and 5, I have the control group. There's only 8 in this group. So on list 6, I can do list 5 minus list 4, and it does the math for me. So now I've got like list 3 in my calculator and L6 in my calculator. That's the only data I need. And I'm going to do one variable stats, and I'm going to get this, and I'm going to get this. So stat, calculate one variable stats. Let's do list 3 first. You can see that it matches up. And it would also match up for list 6. Okay. So that's how I did this. And I took these numbers, folks, and I plugged them in down here. So let me see if I can do this. There, that'll work. So the average goes there, and there. You subtract the averages. And the standard deviations go there, and there, and they get squared. And then sample sizes are 10 and 8. Notice, please, 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 just take a look at this one. Hint, 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 might be on the test. Like how to plug the numbers in, okay? Like only the numerator gets squared, okay? Not the sample sizes. It's not 10 squared or 8 squared. Also, where the world does this come from? This is the degrees of freedom with a 90% confidence. So when you do degrees of freedom, remember I have two sample sizes. I have 8 and 10, so I always pick the smaller one, 8, and do 8 minus 1. So I need to look on my green packet. Where does 7 and 90% confidence intersect on the formula sheets? On table B. Let me clear out some of this stuff from before. 7 and 90% is this one. And sure enough, there's that number that I had, 1.895. Okay. And then again, at this point, I would not do it by hand. I would have my calculator do the rest. This is a 2-sample T interval. Where is that one, Fag? That's number 0, 2-sample T int right there. Now, I actually have the data in my calculator, so I'm going to click data. And then I'm going to put in, if I can remember, mine were list 3 and list 6. And then I have to put my percent confidence, 90%. And there, where did my interval go? Come back. Oop, I went on to the next question, didn't I? Well, that doesn't look correct. What am I doing wrong? Oh, I see it. I changed, I didn't have the right list. List 3. I guess I changed the wrong one. List 6. Nope, okay. I'm fat fingering it. Man, oh man. Let's try it. I keep changing the wrong one. Oh, I see. Hello, Fig. It's over here. It might be late. Okay, there we go. So, um, did it update my interval? That doesn't make sense. Let me just retype 0.9 and hit enter. Well, okay. Oh, I'm struggling. Big time. Oh, look. No, that's, again, this is sometimes when I take answers from textbooks, this is the textbook answer, and I'm like, that's dumb. And my calculator is giving me this 327 and 597. So I'm going to go with the red one. Okay. And they're pretty similar. Okay. Um, conclusion. Oh, let me think of one more thing I just saw. No, it's not the pooling. The pooling makes it a little bit closer, though. You don't pool, so that pool was highlighted, so that did bring my answer closer. Much closer, actually, 0.25 and 6.05. So, there we go. Then you conclude we're 90% confident the true difference in mean scores for those who receive treatment in the control group versus those in the control group is between 0.03 and 6.27 in their scores. So everybody made an improvement because 0 is not in here. All right, last question. Let's land this airplane. Holy smoke, sorry. Longer than I thought here. Um, is this an experiment or observational study? It's an experiment because they imposed a treatment. What did they do? They called people and they either left a message or they didn't leave a message on their phone. And then they waited. So, and did the people call them back? If they called them back, they called that a contact. If they did not call them back, it was no contact. They're thinking if they leave a message, that more people will call back. So based on the data, can we conclude that leaving a message increases the proportion, there's some keywords, of houses that eventually called back and were interviewed. Um, so I define my P's again. Proportion of response rate when a message is left and when no message is left. They are wondering if it increases, so that's why it's a greater than, okay? It's a two sample proportion z-test because we have a null that we're checking. It was stated to be random. Normal, hey guys, I got my 4 counts right here. There they are, piece of cake. Like this is success, failure, success, failure. Independent, these sample sizes are 100 and 291. I mean, yes, that's less than 10% of all the phone numbers or all the phone messages or phone calls that have ever been made. Then you do your statistics. I quickly calculated the probabilities. P1 is when they left a message. P2 is when they did not leave a message. So you can see this is higher than this. But that's where I got these two numbers right there. Your denominator, be careful. You use combined P. This might be on the test. So combined P is when you take the successes and add them up and the sample sizes and add them up. So you get about 66% combined, okay? It's not the smack dab center of these because this sample size is bigger than this sample size. Anyway, you plug those in there. Then I would use my calculator to do the nitty gritty and give me the answer. Hopefully, it jives better this time than my luck last time. This is a um, number 6. Let's put in the data. So we had, um, there's my fractions right there. My 1 is 200. This is why it always helps me to number them. Keep my order straight, because if you reverse this, it does matter. And then 58 out of 100. And my test was which way? It was a greater than test. Swoop. So it's only one-sided. And there's my p, my z, 1.95. My p-value that matches that, 0.0254. Okay, very small. So because it's so low, we're going to reject the null. Okay, which means, right, what are we doing? We're rejecting this, so the evidence is significant enough to support this. We have evidence to support the claim. The proportion who would respond when messages are left is higher than the proportion who would respond when a message is not left. Lastly, just do you remember what a type 1 and type 2 error are? Okay. Type 1 is when you reject the null. You claim there is a difference in proportions, but in reality they are equal. So you reject the null, but the null is true. That's a type 1. Type 2, uh, my handwriting is almost not big enough to read. You reject the null or the alternative, or more correctly, you fail to reject the null. Okay. So in other words, if you are rejecting this, you're saying this is true, but in reality, this is true. Okay. You reject the alternative when the alternative is true. So you will need to know type 1, type 2 error for one question on the test. Sorry guys, that got long. See ya.